So I wanted to do two topics tonight, which is number one, keywords in C. So we're talking basically most of the stuff in this list that you'll actually see someone use at some point in your career. Whereas we won't be going over this stuff, which is the fancy new types that they add. So effectively, before we got bool.h, we had underscore bool, which is basically just the built-in keyword for bool. It's the same thing as hashtag include stdbool.h. Then there's complex, which we're probably not actually going to do, but effectively this is just complex numbers. And I think they include a constant called I that lets you, it basically treats it as a complex number. So double complex z, with complex as the keyword here that represents that this is supposed to be a complex number. I actually don't. I still to this day struggle to figure out how this actually works, where they write the word double and then complex, as in this is a complex number stored as two doubles. But I've never actually been able to figure out. They must literally have complex as a separate keyword for this. And the thing that precedes complex is like the type, right? So float complex, double complex, and long double complex. Whereas each complex number is just composed of two of whatever this type is, right? So float complex is two floats, double complex is two doubles, long double complex is two long doubles, right? So this is complex has always been an interesting type to me, and it looks like they actually have a real keyword for it, and they let you use this capital letter I as a constant. I'm imagining they've done some fancy stuff to actually let this be legal. I still don't really understand how that works. Okay. So the other thing we wanted to talk about was file IO, which we haven't discussed at all yet, which is that's huge. File IO is like massive in C. So one of the first things that we're going to do today is talk in depth about file IO. And unfortunately, I think you actually can. So I think you can demonstrate file IO on godbolt.org. I just haven't done it. I'm way more comfortable doing it in VS Code, so I'm going to be showing it in VS Code. Auto literally doesn't auto literally do nothing. That is, well, okay. auto has a long history. So automatic duration specifier. So effectively, we've actually seen storage class specifiers before, and there's another keyword wrapped up in here that we haven't actually talked about yet, which is the register key. So the two keywords in here that we haven't looked at are register and auto. We have talked about static and extern already, whereas static specifies that the variable is alive and it's placed in data and it lives for the entire scope of the program. Whereas extern basically specifies that it's static duration and links to something that's outside of our program, right? But what we really care about now is auto and register. So long story short, these don't really do anything anymore. They actually, in fact, they did so little that they changed the meaning of auto in C++. In C++ now, you basically use auto to mean this variable doesn't have it's basically like implicit type declaration. So you say auto I equals 5, and I is implicitly an integer, and it figures out what your variable is supposed to be based on what you're initially assigning to it. So it's kind of like exactly like Rust variables in that regard, I guess. Python variables are actually like mutable type, so you can actually just change the type of a Python variable. So you can say x equals 5, and then on the next line you can say x equals a string like hello, and that's god awful. Never do that. Python variables are terrible, but C++ basically lets you use auto in a different way. In this case, automatic duration is basically default, I believe. So the auto specifier is allowed for objects declared at block scope. It indicates automatic storage duration, no linkage, which are the defaults for these kind of declarations. So basically what this reads is that auto is essentially the default variable declaration type. So if I have int main and I have int I equals 5, and I have return 0, so this actually compiles. And do I actually want to compile this? Sure, why not? .exe, nothing happens. Obviously, it's returning 0, though. We can tell that because this isn't erroring. Long story short, effectively, this is implicitly auto. So if I just type auto in I, are they going to yell at me? No, they're not. Okay. So effectively, by default, all of your variables have automatic specification. And then there's, what's the other one? Register, which basically specifies what this actually means is that if you have a register variable, effectively what this is saying is telling the compiler, hey, can you please store this variable not in memory? So you might remember a few days ago when I was doing this out, I actually had the where are my variables stored? Wait, why'd I Google where are my variables stored? That's not what I wanted to Google. What I wanted to Google was C memory, C program memory layout. C program memory layout. So you might remember this fancy schmancy diagram I pulled up, and we were talking about where different types of variables were stored. So effectively, you could say that auto variables are stored on the stack, extern variables are stored outside of this entire contraption, static variables are stored in either the data segment or the BSS segment, and the only other variable type is the register variable type, which actually says, don't store this variable in RAM at all, store it in one of the CPU registers. So for those of you who have already taken 404, you might remember, let's see, I want to search up 404. I want x86 CPU. 86, yes, okay. Give me the list of x86 registers. So effectively, this is the list of registers in x86 CPUs. This is some of them. There's actually a lot more nowadays. There's like I saw 100 plus registers nowadays in modern x86 CPUs. This is most likely what you're running on, unless you're on some fancy new, like I think the new Macs have M1s, and those are ARM based, I believe. So they have a different register count. But anyone who's on like a gaming PC on x86, these are the real registers that you're looking at. So when I declare a variable register, effectively what it's saying is instead of storing my variable in RAM, please store it implicitly in one of these registers. And then you don't actually have to do a memory move from RAM. You literally just have to use the register for that. But this has largely been depreciated by compilers. Compilers do not like supporting you being able to tell them, I want to use this register for this thing. It really annoys compiler developers. So in C++, register has been literally completely just depreciated entirely. No one uses register anymore. But effectively, storage duration and linkage, this basically tells you where the variable is actually being stored. So auto, you can think of auto as the stack. You can think of register as in the CPU. You can think of static as in the data segment. So it's not on the stack, it's in RAM, but in data or BSS. And extern means also in RAM, but somewhere else in RAM. In fact, it also might be a special hardware register if you're on something like a Game Boy. There's more special stuff to this where embedded system developers are going to use extern a lot more. Okay. So that's some of the fancy keywords that we hadn't touched on yet. I mean, we can literally go down each keyword, and if you have any questions about any of these keywords, let me know. If any of these don't look familiar. So break lets you break out of for loops and while loops. Break is actually there's some more semantics to break that we haven't talked about, where I believe you're able to. Oh, is that only in C++? There's no additional semantics to break. You used to be able to actually do a break to a label, I think, in C++, but apparently, I guess you would have to use a goto there, and goto is incredibly illegal. Do not do that. Let's see, where are we? All right, so break lets you break out of a for loop or a while loop. We already know about break. Case used within switch statements. Char, the type char, right? Const, whether or not you're allowed to write to a memory location, or in this case, you could have a const register, right? So register const int I would be an integer stored within a register, which you are not allowed to write to, only read from. But you probably shouldn't do that. Continue statements. We didn't really talk about continue statements, but effectively, continue statements, the second you hit a continue statement in a loop, it skips the rest of the loop and restarts the loop. So instead of breaking out of the loop, it just skips the rest of the loop body and starts the next iteration. Okay, then the default statement, again, you use the default statement in the switch statement, and we're not going to be talking about type generic expressions in C11. We are basically exclusively talking C99 and before here. Let's see. Do, obviously, do loops, do while loops, double, the type double, 64-bit floating point, else for if-else statements, right? Enum is for enum declarations. We talked about those last night. Extern, one of the various linkage types. Float, the floating point type, 32-bit floating point numbers. For for loops. Go to, the most illegal statement in the language, which we didn't talk about, and we shouldn't talk about because this is the most terrible thing you could possibly do. I assume everyone here actually knows how go to statements work, because they're kind of like the I don't know what a good example to this is in other fields. These are basically, the taboo of every programming language. I don't even think most modern programming languages have goto because it's considered such bad practice. But because it basically lets you just transfer control flow from anywhere to anywhere. It breaks the hell out of things if you try to go toing between functions, it's like a nightmare. You would never ever want to use go-tos in any case. All right. Let's see. If statements, obviously, if for if statements. We know if statements. The inline keyword. Okay, so inline, we actually haven't talked about how inline functions work. We have talked about how functions in general work in memory, how effectively every time you call a function, you effectively have to, let me actually pull up Godbolt so I can specify this. So why don't we do something nice and fun and have multiple function calls? And GCC might actually hate me because GCC is known to ignore inline calls. Let's see. All right, for some reason I have to press F12 or godbolt.org doesn't load for me. And they're still not going to load for me? Come on. There we go. How nice of you. Okay, so we're going to very briefly declare a few functions. We're going to declare int g and excuse me. Let's see. We're gonna return number 5, and you know what? To make this more fun, I'll declare the letter F and have this guy equal 5. You know what? Actually, I'll call him G1. Have him equal 5. We'll return G1. Okay. Why are you mad at me? This is okay. Yeah, because there's no semicolon. Okay. All right. So we're just going to declare a bunch of functions here. I'm going to declare 3 functions: G, F, and I can actually use G1 for all of these because these are local variables, which is nice. G, F, and H. And the one thing that's going to be different about each of these is instead of this, we're actually going to call the previous one. So I'm going to get the value of G1 from G here, and from this one, I'm going to get the value from F. Okay, so now this is basically just calling up some stack and setting some variable equal to something. And I'm going to change my output to my preferred ASM syntax. And I don't want to talk too in-depth about the ASM, but effectively, I just want to show off main here. Int main. And in main, we are going to call, I'll just do return h. Return h. So traditionally, when you call a function, you're going to see this call instruction right here in assembly. And effectively, you don't need to know any assembly for this, but effectively what this does is you can see it says call h, and you're going to see we have this h up here. And effectively, this is saying, all right, we're going to call this function called h, and here's all the code for h. So this is basically transferring control flow from main over to h right here, and then it's going to do all of these other instructions based on what we've specified here, right? And we can see here that we're calling f in h, and we can see that in in f we're calling g up until the top here, right? And then finally this thing doesn't call anything. Now, what the inline keyword does is actually removes the expensive overhead of doing a function call, because what it says is we can literally copy and paste whatever code you wanted inside of the function that you're already in. And you can only do this in certain circumstances. So, for example, when I specify that G should be inline, what should be happening is it should specify G1 inside of here now as something else. It would have a different name, obviously. And it would say, okay, G3 equals 5. And then because I see you're returning G1, I'm going to say that you equal G3. So effectively, all of the code from G can be inlined into a separate function. So if you declare an inline function, it basically tries to do this implicitly. So if I say inline in G right here, we see that effectively what's happening here is that the entire G function has been deleted. There's no G function in our header in our assembly here anymore. We see that effectively. Oh wait, they're calling G. Why are you calling G? What are you doing? There is no G to call. What do you mean call G? Why is there a call G here? G, good, good. But like, okay, but there's no G. I can't be crazy. I can't be the only one who sees the fact that there's no G here. Do I have to enable GCC is very annoying with all of this. Okay, and here the second we try and do any optimizations, they immediately see that this is all just tied up to G and returns 5 for all of this. So inline functions in general aren't particularly useful. I'm very scared about which one of you invited me to Mommy Squadron Part 2 Return of James Hullabaloo? I know that's one of you guys. No one else would invite me to this Discord chat. But I'm gonna move that over because that is not we are talking right now about inline functions. So back to inline functions. Please stop inviting me to strange chats while I'm doing the C workshop. Thank you. Okay. So effectively, what inline is supposed to do is implicitly move the code that you have in here into whatever else you're in. I'm gonna see if I can force this with something that's nicer. I'm gonna do a void, and I'm gonna get a printf in here. So hashtag include stdio.h, and we are literally just going to have a function called hello, and all this function does is print hello, nothing else. Printf hello. Okay. So all this function does is print hello. Okay. And I'm going to then call hello from here. Please inline my function. How are you calling hello? It's been inline. So the second I switch it, you can actually see the difference between the inlining though by the implicit inlining when I enable optimization level 1. Because effectively you can see here that in main, I'm doing call hello, and the second I enable optimization, so I do O1, we can immediately see that inside of main, we're calling printf. So now instead of calling to hello, we're just calling printf. It's literally just copying this code right here into main in place of hello. So it's basically replacing hello with the line printf. So you can inline functions in the event effectively that you are allowed to in the event that you're not breaking anything effectively. So inline functions sparingly, but in the event that basically you use your function as just a procedure call, and there's not, depending on the parameters and everything, if you're not passing any pointers or anything, inlining is perfectly acceptable. And most people will inline a ton of functions, but that can cause its own issues. So I would say use inline rather sparingly, and compilers will do inlining implicitly nowadays. So some people will just say never inline anything because there's no point anymore. Especially in C++, they've given new meaning to the inline keyword. But effectively, we don't really care about inline. We just want to know what inline is. And there might be a question about that on the LinkedIn skill assessment, but we're going to take a look at all the LinkedIn skill assessment questions tomorrow night before you guys take the LinkedIn skill assessment. I have a list of like 10 of them. They may, or I actually think I have like 15 of them. They may or may not actually be the questions that you actually get on the LinkedIn skill assessment. We're still not sure about this because we stole them from Dawn when Dawn took the C LinkedIn skill assessment. Okay. Um, back to what we were talking about. We are going to int obviously declare integer variable. That's the type. Long is another type. Register is a storage specifier. Restrict. I've never seen a restrict. I literally have never seen anyone use this keyword in my entire life, and they've apparently given it new life in C23. The fact that I've never seen this keyword in my life means that you're never going to use this keyword because I've never used. Okay, so this is like an alternative to CV qualifiers. Several qualified versions of the type, one, two, or all three of const, volatile, or restrict. Okay, so it's a CV qualifier type. Yeah, but like, what does it actually do? Restrict semantics apply only to L-value expressions. For example, cast a restrict qualified function call, returning a restrict qualified pointer. Give me an example of when you would use this. I fail to understand why you would want what this actually is. I'm gonna say that you just don't ever need to use this because I can't actually figure out what it is. I'll go read about that later, but I can basically guarantee restrict won't be on the LinkedIn skill assessment, so not really an issue on that one. Return obviously is to return from a function. No biggie, no big surprises there. Short, the type short 16 bits or 2 bytes. Signed is specifying whether or not a numeric type can be negative. So if you want to have one of your types have negative values, you would use signed as a prefix on that. Same with unsigned down here. Those are the signed specifiers. Size of is the special operator that tells you how many bytes your type is or variable. So we might recall from back in the good old days. I don't know how much we actually went over this, but effectively, I'm going to just do print %d right here. And what we're going to do is just print out the sizes of some various types to demonstrate how this works. Effectively, this is the size of keyword, and basically you use it as if it's a function call. And you can either pass in a type, so I can say size of int, and it tells me 4. Size of float should also be 4. We can see that's 4. Size of long should be 8. And again, this is in bytes, not bits. If you want the byte size or the bit size instead of the byte size, you multiply by the size of a byte, which is 8 bits. So we can see that the size of a long in bits is 64. So any type, including custom struct. So if I declare a struct here, struct, and remember that structs are additive structures, so we reserve memory for every single member. If I declare int a, b, c, d, e, f, we know that each of these members is going to take up 4 bytes apiece because they're all ints. I don't know why I put parentheses there. I'll call this struct s, and now I ask what the size of struct s is. We are going to see that it is going to be, let's see, s undeclared. First, because I actually have to type out struct because I didn't do a typedef. But so now we can see that this struct is 24 bytes long, effectively, because each of these ints is 4 bytes. So 4, 8, 12, 16, 20, 24. Easy peasy. So structs are additive. If we do this on a union, though, so remember that a union always has the size of its largest member. So in this case, if I actually have an int a and I do a long b and a short c, what's the longest member here? Well, it's b, which is size 8 bytes. We can see that, though, if I do it additive again right now, effectively what this is saying is 4 plus 8 plus 2. And I'm actually kind of surprised that this, what, you're saying that this is 24? It's 4 plus 8? I don't think 4 plus 8 plus 2. How are they doing storage on this? There's some weird alignment stuff, so this struct might actually be spaced out over a different size, effectively. You might be able to rearrange this if you rearrange members, but I don't want to mess around with. Yeah, so that's something weird that you just saw there, where the order of this actually changes stuff. So if I put the short down here, this struct is 24 bytes. But if I put the short above the long, we see that it's 16 bytes, which again, that's still wrong because long, it's not as packed as it should be because of, long story short, there's memory alignment stuff where they have to specify that a struct integers can only be aligned on certain bytes, et cetera, for all of these different types. Right, because a long has to be aligned on every. There's a long story to why all of this has to be in a specific way, but we're not gonna get too deep into this because they'll never ask you a question on this. But what I really want to show was the union. If we have a union here called S, I should be able to get the size of union S here as the size of its longest type, and the size of the longest type of in this union is long, which is 8 bytes, right? So size of union S, easy peasy. And the other thing that we haven't discussed, at least I don't know if we've actually used size of like this, but effectively, if you declare a structure or a union or a variable, you can actually use the name of a variable and it will know the type of that and it's able to print that out. So if I do size of S, which is the union object effectively, or if I do this as a struct and I call you struct S, we can actually get the size of the entire struct right here. Anyway, let's see. The other thing, so that's really all you can do with size of. There's not much else. I think you can also size of enums as well. So if you have an enum type, you can get the size of that. I think enums are almost always going to be ints. One fancy thing that I actually don't think we talked about was the declaration of inline anonymous structs. So something like this. Let's see if they let me. So if I do this, this, and this. Now, warning, unnamed struct. Yeah. Am I allowed to do this in C? I know I'm allowed to do this in C++. All right, let me do it. Let's see. Am I allowed? I am allowed. So this is actually an anonymous struct declaration. So basically, you can declare variables like this. So I could literally just be like, oh yeah, struct in A, B, and C, and then give this a name inside of my function. So I could call this like my struct, and this is basically declaring an object of this type that we declare right before we actually declare the object. But please never do this. This is really jank and considered really bad practice. But I have seen it. I have seen it done before, and obviously I can get the size of this as well. And this is actually why structs have to have that semicolon on the end, because you can use struct statements for definitions of variables inside of main. So when you actually declare struct out here with a name, what you're really doing is actually assigning this as effectively a global that doesn't actually have a value, declaring that this type exists. Anyway, I think we talked about that a few days ago, but not in the context of anonymous structs. That's what that's called, when the struct doesn't have a name and you just initialize a variable off it from it without actually giving the struct a name. Anyway, so that's size of, and we're not actually going to do size. Oh, so the other thing that I don't think I discussed with size of. Let me. Where's Compiler Explorer? Ah, beautiful Compiler Explorer. You can do size of expressions. So I actually think you can do stuff like size. So what if I do like size of 1? Okay, so 1 is an integer, so it says it's 4, right? So they basically default interpret all numeric constants as integers. But I should be able to screw with this, I think. So this is an expression. And then can I get something that evaluates to something like weird and long instead? Like if I make this like really long and I say 0x FFFF until all right, so now it places this in a long. So effectively you can size of an expression without the parentheses, and this entire expression returns the size of whatever your expression here is returning. So I could also do plus, and this would return some constant that we could measure the size of. Probably can also do the same things for strings. So size of hello literally being 6 characters if you include the null terminator, which they do. So size of hello, the expression hello, is 6 bytes, right? And that makes sense because it's literally a string of size 6. Anyway, that's enough about size of. I think we've decently covered that. Size of is probably one of the most used operators in C, though. Static, again, we talked about static. Static, all static says is that, so we talked about static on what? I think strings and things day. But effectively, all static does is tell you that, okay, we're actually going to be storing our variable in. I've lost my beautiful. Memory map. C memory layout. Come on, give it back to me. Yeah, so effectively all static does is it says instead of storing your variable in on the stack when you call a function, you're storing your variable in the initialized data or uninitialized data segment, which means the value of that variable lasts for the entire program and is never at risk of being overridden, even when you call the function. And again, it doesn't actually reassign the initial value. And you use that obviously in place of globals. It's better to use statics than globals. Anyway, moving on. Struct, we've done structs. Structs are the objects of the C programming language. Lets you combine different data types into one big data type. Let's see. Switch statements. Obvious, we know switch statements. Oh, we've never talked about typedefs, which is kind of depressing, honestly, that we never talked about typedef. Typedef is a very, very simple, um, very simple command. All typedef does, typedef and then the name of your new type. This basically lets me declare new type names. So if I type def name to int, now whenever I actually use name as a type, so if I say name I equals 5, it's basically just letting us use the word name as this int. It's basically equivalent to doing hashtag define name int. Um, they're actually really similar. It's almost uncanny. The difference being that this is a C statement and this is a preprocessor statement that would literally replace name within. The thing that's good about this though is you can actually do typedefs of structs, and that lets you basically get away with using structs without the struct keyword, as well as unions and enums. So effectively, when you actually do typedef struct blah 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 and then as thing, so I'm going to typedef struct, I guess I'll have what it be person. So what are some qualities of a person in age? Const char pointer name sure person. Now when we declare this struct, we only have to declare this as a person rather than struct person. So I can say person p blah 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 blah. Effectively, this lets us get away with, let's see, what are they mad about? No semicolon at end of struct or union. But it's a typedef struct. Oh, they want it after this. Okay, I see how it is. Okay. Long story short, this actually isn't printfing anything. I don't know why I have that there. But effectively, this is letting us use person instead of struct person. But you can also do fancy stuff like this and actually define the person here as well. So now when I do this, I can use either struct person or person. So I get to pick and choose whether I use struct person or discard the struct keyword altogether when I actually declare a struct object. And obviously, those of you who use C++, they've removed the need to actually have the keyword for your structure class in front of it in C++, and basically just had this be the default, as if you were typedefing the entire thing. But so the typedef keyword, again, is literally effectively just defining that type as whatever it is here. So again, even this is exactly equivalent to me saying typedef or define person as struct person age blah blah blah, except I don't actually think I can do that. I'd have to do an anonymous struct here. And what are they going to yell at me for? Yeah, keep yelling at me. There's nothing to yell at me here for. Unnamed struct. Is it because I'm doing the typedef there? Yeah, it is. Okay. Long story short, this is those two statements are equivalent. So the typedef and the hashtag define blah 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 blah. Right. So the typedef is just a literal semantic statement. So the typedef is taken care of during the compilation phase, whereas the macro version is taken care of during the pre-processing phase. There's arguments for or against either way, but effectively you can just view this as the typedef as a text replacement. Sometimes there's benefits to using the typedef, but we're not actually going to go into those. Okay, so typedef, union, we covered unions yesterday. Unsigned, again, the opposite of signed. This means that your numeric type will never be negative. The void keyword is used in two places. The void type, which is void characters. You can also, if your function doesn't take any parameters, you can say that it is a void function. So you can literally write the word void there, and that's an alternative way of saying that the function takes no parameters. Most of the time, though, you just prefer to leave that out. In fact, it's so unpopular to do that nowadays that I don't even think I learned that you could do this until like last year. You almost never see that. Let's see. Where do I want to go? What was I talking about? Okay. And then void pointer, though, is going to be the main place you're going to use the void type. Void pointer being a pointer to something that you don't know the type of at the moment, but you can cast void pointer to any type of pointer, which is what makes it so powerful. Obviously, then the other use is void functions, which don't return any value, right? So next is the volatile keyword, and we discussed the volatile keyword recently. I think this was like a day one discussion. Effectively, a volatile keyword, at least not to get into the insane technicalities of the volatile keyword, means that you're telling the compiler, at least in 99% of the time, you're telling the compiler, hey, this has some magic thing that's going to twiddle it. So, say like a hardware signal that's literally supposed to twiddle this memory location. Please don't touch this. Like, do not optimize this out of existence. So, for example, if I did something, a good example of this would be if I did something literally like this, where I said, all right, int I equals 0, done. And now I'm never going to touch this I again, and I'm going to do something else. So if I actually look at the output of this on the compiler, we can see that when we're doing no optimizations on this, the statement, let's see, demangle, good, good. So we can see that this actually does compile to an ASM statement. So this int I equals 0 exists, right? We're doing this, right? So there's actually an instruction that literally puts 0 into I right here. Whereas if I turn the optimizer on and I say optimize max optimizations, you can see that it yeets that variable out of existence and says, we're not even going to run this statement. And effectively, this XOR here just means set the return value to 0. So we're not actually going to go into how this works, but effectively, whenever you XOR something with itself, it sets the register to 0, and EX is the return register, blah, blah, blah. Doesn't actually matter. But what we really care about here is that effectively they've optimized this variable out of existence by typing volatile as a qualifier here. We say, no, you cannot eat this out of existence. You have to set I equal to this thing, no matter what, even if you don't see that we're using it. And the reason you would do this is because there are instances where you want to see the value of a variable, no matter what, and the compiler wouldn't know that you would want to see it. So this is if you're linking to some other program, blah, blah, blah. Multi-threading, you see a lot of volatile because you're accessing a variable between threads. And the compiler is like, wait, what do you mean you're accessing this? I didn't know that you were accessing this, blah, blah, blah. So volatile is one of the rare keywords that you're going to see. I use it a lot for debugging when there's like a variable of return value I want to see, and the function itself doesn't actually use the return value. So I have to declare it volatile to see it in the debugger. Yeah, you can see that by putting the volatile keyword, even with maximum optimizations, we save this variable's existence. So here we see it optimizes out of existence. Here we see with the volatile keyword, it still exists in the code. So we're forcing 0 to be assigned to this, even though it's never used. Okay, so back to keywords. We're coming up on the end of keywords here. While, which is just while loop, easy peasy, right? Nothing too fancy. Hang on, I have Discord closed. I actually don't know if anyone said anything in chat. No, okay, good, we're good. The other things that we wanted to talk about were some of the the preprocessor keywords that I didn't get to talk about. So there's probably only a few. So hashtag if just checks if something has been defined or not. Elif, again, it's the else statement for if something's been defined or not. Well, else is the else statement for if something's been defined. Elif is the else if of defines, preprocessor defined. End if is the keyword that basically ends your expression. So conditional inclusion is what they call it. And they group all of these together. If def, if end def, if def, all of these conditional preprocessor macros that tell you whether or not to include chunks of code. The other thing that we want to talk about though is, so we did define undef, include. So the ones that we didn't look at are probably hashtag line and hashtag pragma. So hashtag pragma is basically entirely implementation defined. What you primarily use hashtag pragma for is, you know how you have to write include guards for libraries? So good thing I actually have an example of this with this linked list library. So on Monday, we had gone over writing include guards. So you can see here I say hashtag if and end def linked list.h, then you define linked list.h, and then end if at the end of the file for this big if statement. So basically, this makes sure that this code here is only included once, no matter how many header files it's included across. And we can see that if we remove the include guard and try and compile this, we are immediately going to start getting errors. And the reason we're going to get errors is because I made this special library here. So this includes linked list.h, does something with your linked list. And then in our main, basically we're including linked list.h twice, right? Because we're including linked list.h in our main driver code, but we're also including lib.h, which includes linked list.h. So if I actually go in and try and compile this in homework 3, and I gcc driver.c, we are going to see that effectively, and I'm going to actually -c -o driver dot because I don't want to actually deal with okay, so effectively we can see them yelling at us because we have multiple inclusions of linked list here. So the way that you prevent that, obviously, is with the include guard in your header file. But the other alternative way of writing the header guard is to literally just say hashtag Pragma once at the top of your file. And this basically functions as an entire include guard for this file. So now if I compile this, this should actually work. Well, we're about to find out if that's true or not. Yeah, that works. So effectively, hashtag Pragma once acts as an entire include guard. It functions as the hashtag if def, hashtag if end def, hashtag define, and then the hashtag end if at the end of the file. But it's the preprocessor takes care of all of this for us. So this is actually non-standard, but it's so common that it may as well be standard. Every major C compiler implements hashtag pragma once. Yeah. Okay. So back to the grind. What else do we have? Pragma was like the last thing I wanted to talk about. We didn't talk about hashtag line. This changes line numbers, and we don't ever actually want to do this, and you'll never actually use this. Effectively, the reason that this might be useful is like this example down here where they're doing an assert in assert.h, which we're never going to use. And they're basically saying, oh yeah, we're going to say that this is line 777, and then the assert basically gets the line that you're on where the error happened. So even though this is actually like only line 5 of this file, it's going to say that it's line 777. So there's not really many reasons that you would want to do this other than for debugging reasons, but you almost would never want that. Okay, so that's basically every single keyword in the language, unless we want to start talking about some of these non-standard ones down here, like align as, align of. We're not going to mess around with alignment. Alignment is the reason that our struct was screwy when we actually went to look at the size of our struct, and it said, oh, your struct is actually this big, even though the internal types are only using this many bytes. we actually need it to be this big instead. And there's a long story about why it has to do that, because certain types have to have certain alignment boundaries, and you have to handle that with alignment. And we're not actually going to go too in depth on that, because for our purposes, alignment doesn't really matter. But if you were an operating system developer who had things that had to be in RAM in a specific way, or if you're writing a Game Boy game, for example, where every single bit of memory counts and you're an embedded systems developer and your struct has to be all squished together and you don't care about alignment, then you have to actually start caring about alignment. But for the normal programmer who's programming high level applications, alignment is a non-issue. But the second you start trying to program an operating system, alignment becomes a very very important issue that you have to deal with. So that's not really our anything that we're going to worry about. We're not going to worry about atomics either. Atomics are beyond the scope of this. Multi-threading is beyond the scope of what we're talking about. In fact, I don't think there'll be any multi-threading questions tomorrow. Let's see. Imaginary, complex, we aren't going to be touching on those. You can know that they exist. So if you ever want to do complex math and see a Mandelbrot set generator, for example, complex.h is your friend. No return. I didn't even know they added this, but this is all C11 stuff, and all of the C11 stuff is beyond what most people use. I don't even think you're allowed to use C11 on like real C projects. I think what C version is the Linux compiler is Linux on? Version is Linux. All right. Oh, look, they actually upgraded to C11. Good for them. I wonder how long it took for them. So C99, though, which is what we've been looking at, has been the standard for ages, and most people are going to say only use C99 and everything in C11 is silly and unnecessary. At least that's what like the true C purists are going to say. It's so rare that a new version of C comes out. Like you got C99, C11, and then C23. So it's on like a 12-year release cycle as opposed to a language like C++, which is on like a 4-year release cycle. So they're coming out with like a new version of C++ with tons of new libraries like every 3 years. C is insanely hard though to get changed. It almost never happens. And everyone who actually uses C grew up even before the time of C99. So they don't even know half of these keywords. Anything here that's marked with since C99 means it was added in C99. Anything marked in since C11 means it was added in 2011, effectively. So it's kind of crazy to think how long the legacy of C is and how far it goes back, though. Anyway, any questions about keywords before we move on? Because I'm going to now switch over. It is 9:07. We can switch over and talk about file I/O, which is a lot of fun. Not really anything special. It's pretty straightforward compared to everything else that we've been doing so far. And I'm going to have to go over here and demo it in here because I don't know how to do it in Godbolt. I know you can do it in Godbolt. I've just never done it in Godbolt. So instead of trying to learn how to do it in Godbolt on the fly right now, I'm going to do C file IO over here. So the file IO stuff is actually when you include stdio.h. This actually gives you all the file stuff too, which is really nice. So stdio stands for standard IO, right? So standard IO and file IO is included in that IO, as is printf, et cetera, right? So effectively, file IO in C is actually rather straightforward. I think, you know what, the best move right now is actually just going to be to go to, where's my libraries? Hello? Preprocessor, statements, expressions. Okay. No, yeah, okay. C headers. This is what I want. So these are all of the C headers. As you can see, we actually haven't gone over that many of them. Um, so assert.h, you know what? We may as well just go over what every single header is right now while we're sitting here, right? So there's a lot of fun headers here. For a lot of like weird stuff that you'd never think that you'd actually be able to do. So assert.h is basically just testing your C code. This is assertions. And this just throws errors essentially if something is off in your C code. So conditionally compiled argument. So conditionally compiled, this is good because basically what this means is you get to decide whether or not your final version actually has asserts in it. So that's why the assert keyword. It's not a keyword. I think it's a function, right? So aborts the program if the user specified condition is true, and you can disable assert for release builds, which basically means it doesn't compile to anything. And yeah, okay, so it's a function macro, right? So effectively what this means is it's hashtag define and then parameters into this, right? So you can actually see right here how they do this. So if defined n debug, which means no debug, then they define assert as literally not doing anything. Right here, you can see it's void 0. Whereas if debug is defined or n debug isn't defined, then assert condition is going to compile to something that actually does something, and its implementation defined. But what this means is you're not generating any additional assembly by putting asserts in if you don't want to. So that's asserts in C. Complex.h, pretty straightforward, complex numbers, not our cup of tea though, not what we're going to be covering. C type, oh boy, we don't really want to talk about C type. This is basically just like a bunch of nice helper functions. You might remember some of these when we were going over string.h, because string.h has a lot of nice functions for dealing with strings, whereas C type basically includes all of these functions that let you check different properties of things. So let's see, the 2 lower and 2 upper are actually in here. So this is like converting characters between uppercase, lowercase. Then you have all of these fancy schmancy functions. Basically, is digit, checks if character is digit, is lower, is upper, is X digit, is space, is blank, is print, right? So there's a ton of stuff. And then there's all of these weird comparisons where you can like check different character, and like they have this whole table here of like if things or different things is punched. So it says, okay, all of these are punctuations, blah, blah, blah. Like, there's a ton of weird comparisons you can do, but like half the time you would just implement this yourself because you're too lazy. Like, I would, if I wanted to figure out if something was a punctuation, I just write my own function in like 5 seconds rather than having to come and look it up and include C type. C type is kind of a meme, to be honest. I've never actually used it. Um, Erno is macros that represent error numbers. So we're talking about, do they actually have the list of errors that they include? Okay, so this is like standard. So edom, esec. So this is actually like, essentially, I would think of this as like enums, effectively, even though it's not enum, it's a chain of macro definitions. But effectively, Erno lets you have access to like operating system specific error conditions, blah blah blah. FENV is for the floating point environment. We're not going to worry about this. I think they also, yeah. So there's also a bunch of the exceptions that can be thrown by floating point math, and you're able to handle these as signals. But again, that's beyond the scope of this. I don't think we really talked about signals during this series. There was a office hours session that signals were discussed at, and division by zero signals were discussed at, but not really our concern. Float.h is limits of floating point types. So this is basically like what's the minimum float value, what's the maximum float value, blah blah blah, tons of fancy other stuff that you can use. So here you can see just them trying to print out all of the different constants that this offers on some system. So obviously all of these are system dependent, especially if you're on an embedded system. You might not be able to use certain types of floating points, blah blah blah. And this is how you actually check that programmatically, is float.h. Int types is conversions between different integer types, and I guess they also include my nice, oh no, this is std int. But where's my conversions? Should be std int as well. It's like limits, same thing as float.h. And they said they had conversions. I've actually never taken a look at the conversions. I guess they're doing, let's see, in int types they have fprintf, which, yeah, okay, so this basically converts between different numeric types. We're not really that concerned about that either. When we want to convert between numeric types, it's so much easier just to do a cast. But there are specific situations where you might want to do fancy stuff like this. ISO 646. Oh, this is a fun one. This one gives you special operators, so you can write and eq, And this is just operator macros. So effectively, someone has a hashtag define bit and as this symbol right here. That's all this does, is just a bunch of defines to define these certain words as operators. So kind of stupid, to be honest, but ISO for what was it 646 basically mandates that these exist, and this was a C95 edition, but it wasn't original. Limits.h is basically the same thing as int.h, at least in my understanding of it. What we have here is basically the sizes of different ints on the system. Again, not something we actually care about. I'd say the number one library that you probably want to care about is stdio, right, which gives you your input output. stdlib, which is probably one of the most important one, provides you the malloc, realloc, free, blah blah blah. So all of the really important stuff is in stdio and stdlib. String.h provides you all of your string algorithms, which again, very useful. Math.h gives you square root, etc., so you don't actually have to write your square root algorithm yourself. We were actually supposed to talk about math.h today, but in the interest of time, I don't really want to go over. So as you can see, there's a ton of math functions in here. Most of these you probably already have the general idea of. ABS is the absolute value of a number, right? Abs for ints, labs for longs, LL labs for long longs, right? So most of the time when you do absolute value on an int, you're just going to be getting that. There's also fabs. So most of math.h is for floating point numbers, right? So fabs is it's it is fabs for floating point absolute value, but some people like to call this fabs, which is kind of fancy. Not gonna lie, I should start calling it fabs because it's funny, but effectively all this is doing is returning the non-negative version of whatever floating point value you have. This is absolutely of one operation because floaters represent their sign as a single bit, so you're just flipping a single bit from this effectively conditionally. But all right, the next thing we want to take a look at is we literally have modular division. That's unnecessary. Fmod for modular division. Again, I don't really fully understand why you would want to use fmod rather than our glorious percent operator, but to each their own. Remainder, again, let's see, computes the remainder of floating point division operating, computes the signed remainder of so this, I guess this isn't a okay, so remainder and fmod are actually separate because there is a signed going on here where effectively you might want signed if you're doing this on a negative number, but let's see, rec quo computes the remainder as well as the last 3 bits. So this is like all division remainder quotient. Okay, okay. FMA computes fused multiply add. I've never even seen this. You'll never be asked a question about any of these. The main things that you would use are fmax to get the max. You could use ABS for absolute value. So let's talk really quickly about things that you'll actually see people use frequently. Um, FABS for absolute value. You'll see max to get the maximum of 2 floating point values. You'll see min to get the min of 2 floats. You'll see nan to get nan values, so you can actually compute with nan, which we rarely want to do. There's certain instances where you could accidentally return a nan from an operation, and you want to make sure that you're not actually using a nan, and the only way to actually do that is to use the nan function effectively to report whether or not you actually are nan or not. All right, so exp for exponential is the exponential function, so e to the power of x. 2 to the power x is exp2. You use that all the time. What else do we have? I've actually haven't used like half of these. I use log for ln, and then log 2 for log base 2, which is useful if you don't know why we might want to use log base 2. There's actually a lot of good reasons to use log base 2. You can use this to speed up some of the binary tree algorithms, and you can be like, oh, we have to be lower than the size, basically. Anyway, pow is the power function. So this is useful because this is float pows. So effectively, it's kind of hard, unless you know complex numbers and you know that the log of a No, it's so the power of a real number is equivalent to, I believe it's e to the power of a times ln b is equivalent to a to the power of b. I could have that backwards, but effectively that's how you have to compute floating point exponents and with a float base. So if you don't know that, it's useful to have a POW function that you can use yourself, and it's probably honestly preferred to use the math.h POW function rather than write your own fancy POW function. So POW, square root, obviously, this is all in math.h. Hypot is pretty fancy. This basically computes the hypotenuse of a triangle, right? So the square root of x squared plus y squared, very useful to just you call the hypot function. I do that all the time. Then trigonometric functions, so you get sine in here, cos in here, tan is in here, arc sine, arc cos, arc tan, very fancy. Hyperbolic tangent, cosine, blah blah blah. I rarely use this stuff, but this is useful for the engineers who are using this for various types of computations. Let's see. ERF for the error function. Again, not something that you typically use. The gamma function as well. More rare high-level math stuff. Ceil and floor you use very frequently, which again, ceil rounds up, floor rounds down, and trunc is basically real rounding, right? Same with round. So rounds away zero from zero in halfway cases. Okay, so this rounds to the nearest integer not greater in magnitude than the given value. I'm so wait, this just rounds up. Trunc rounds. I thought trunc rounded down. All right. Anyway, here's round nearby in. So there's an underlying rounding mode. Don't worry about that. The only things that I would use are basically ceil, floor, and round, or what I've actually experienced in 6 years of C. Um, the other thing I want to talk about is, so we're going to ignore all of these, never use these, never use these. What else are we looking for? Where is, I could have sworn random was in here. Did I miss random? Or is it, do I have to include rand.h? I thought there was a rand in math. I guess not. All right. Where is my, so the three libraries that I've said are the core libraries so far are stdio.h, stdlib.h, math.h, which I somehow missed up here. We don't want to do set local. We don't want set jump. Signal.h is for signal handling, which again, beyond the scope of what we're discussing. STD align, again, beyond the scope of what we're doing. STD arg, we actually went over yesterday, gives us access to have varadic functions where we can have variable number of arguments for our functions, right? So we can write printf-like functions all by ourselves, which is very nice and fancy. The other thing was, what else do we have here? Oh, stdbool.h. We've used stdbool.h. stddef is actually kind of fancy. It gives us like common defines. In fact, most things actually include this. This gives us stuff like size t, which I was talking about before. You always want to make basically your pointer size, not pointer, your array size should always be size t. It's the largest unsigned integer type on the system. Null, which is always going to be a void pointer effectively. So this is when a pointer doesn't actually have a value. They also define bool. They basically include bool in here as well. So that's just common defines. But you almost never define that yourself because everything includes it for you. It's like the first thing that's included. Let's see what else. String.h I said was important. The only other thing in here that seems particularly of note would be time.h, which basically this is all of the date time utilities. This lets you get the current system time. What time is it right now? You can print this stuff to dates, blah, blah, blah. You can do some fancy stuff with time. But we're not, again, that's beyond the scope of what we're talking about. And then all of the fancy UTFs. So this is like Unicode utilities. And then this is more character utilities. It's a lot of character utilities. But as you can see, the standard library is actually kind of small compared to some other languages. You don't get that many functions written for you. The brunt of the functions that you get written for you are effectively in stdlib and in std or not even std, in string.h. So string.h, stdlib, and stdio. Those are like your main things, and then math if you're doing any kind of fancy math calculations. That's really the main things that you're going to be including if you're just writing basic programs. Oh, and your random numbers are actually in stdlib. So I don't think we ever actually did random numbers. Random numbers in C are actually really, really straightforward. So I may as well demonstrate um, how random numbers in C work really quickly. So effectively, the way that random numbers work in C, I'm gonna hashtag include stdlib.h. And effectively, the way that this works is, so I'm going to do printf and then print out a float, and we're actually going to print out this float right here, f, and we're going to call the rand function. So this is a function that doesn't take anything in and just prints out a random number. So I'm going to go over to an execution only window, and we can see that this is printing out 0, 0, 0. I find this incredibly hard to believe. Does rand return a double? The only way I can see this feasible is if this is a double. Int. Wait. Oh, that's right. Okay, this is. I'm thinking of a different language. What language has this as a float function? I think it's JavaScript. Like if I do, I think I have to include a math thing for JavaScript. Is it math.random? And this should return, yeah, okay, I'm thinking of JavaScript's math.random, which returns between 0 and 1, a random float between 0 and 1. So what I actually want to do here is actually print out %d to print out a random number. So effectively, in C, this is very straightforward. They give you the rand function, and this will return a random number between, it's a pseudo random number between 0 and our highest guy, which is going to be rand max. So this rand max is basically a constant that's the highest possible random number that can be generated. So if you want a random number between 0 and 1, a random float between 0 and 1, you actually have to cast one of these to float, otherwise it's going to be integer division. But effectively, this will generate consistently every single time, rand max being the highest possible value that rand can produce. And then rand producing some value between 0 and this. So the lowest possible thing that this could be is if rand is 0, then this expression evaluates to 0. And if rand evaluates to rand max, then this is 1. Every other time, this is going to evaluate to something between 0 and 1. So this is how you generate a random float. So obviously, we can do some fun stuff with this. Let's see. The only the downside to this is that effectively, no matter how many times I run this program, I'm always going to get the same thing. I have to seed the random number generator with the srand function, which effectively what this does is provide some initial value to the random number generator, which lets it decide the number. But we can see effectively, if I do this, if I have the seed as 1, 2, 3, then it's going to be this 0.060051. If I change this to 4, this changes the random number. But if I go back to 1, 2, 3, it's the same thing it was before. So to have this be truly random on every single run, what you normally have to do is actually use the time to seed it. So you actually take the global time and you seed the random number generator with the current clock time. But we're not going to do that. That's beyond the scope of what we're discussing. And I want to get to the file system because we are at 9:30. So let's talk files, 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 and stdio. I kind of went off on a huge tangent there and didn't get to talk about files. But now we are going to talk about files, and I'm going to go to stdio so we can actually discuss stdio. Come on, stdio dot h input output. Yes, yes, yes. Okay, so the first thing that we're going to want to talk about is file and fopen. So file here is a very special type, which, as you can see here, they do it as a typedef. So they say typedef unspecified file. What unspecified means is that this is implementation defined. So they get to decide what this is. Your operating system, your compiler, your vendor gets to decide what this actually is. But effectively, in effect, this is always going to be some numeric type, but we really shouldn't peek in here. It's very well defined on Linux. More proprietary operating systems kind of followed in Linux's footstep. Effectively, what this is it represents the actual file object. And effectively, what we're going to do is we're going to have a pointer to this file object. So we actually don't really need to ever actually use this pointer directly. It's just something that we have to hold. And you can basically think of the pointer to the file object as some magical value that lets all of our functions know what file we're actually talking about. So the first thing that we're going to look at is the fopen function. So the fopen function opens a file in a mode. So you're going to see the first parameter here is a const char pointer file name. So this is the actual name of the file on the operating system we want to open. And then you're going to see another const char here, and this is the mode. And effectively, what this actually means is what we are going to be doing to this file once it's open. So R is to read to a file, W is to write, A is to append, R plus is to read extend. So this is basically to read the file from, let's see. So there's a lot of different. I've basically never used read plus. Effectively, what I like to do is you can do combinations of these, and there's also B to open in binary mode. So by default, you're writing characters to a file, but you can also write raw binary data by appending B, and you can combine multiple of these into some big fancy thing. I wish they would do an example of them doing a more fancy thing, but effectively, you could do RWB, which is read write in binary mode. You can combine these into more fancy access flags. Okay, so I think what I'm going to do is I'm going to demonstrate that. So also you can see here that they have so action if file does not exist. If you try and open a file that doesn't exist to read from it, it fails to open. But if you try and write to a file with W that doesn't exist yet, it actually will create the file on the fopen call from default. So you're going to see that this actually returns a pointer to an all caps file object. And this is actually just basically, again, the file pointer serves as our identifier for the file that we've opened. So the way that we're going to do this is we're going to say, I don't know who I actually want to read to. I'm going to create a little text. You know what? I'll write and then read. So let's do writing first. So first things first, I'm going to have file pointer my file. And I'm going to say that this equals fopen. And then I'm going to have my file be called hello meme dot exe, not exe. Why would I have it be exe? I'll have it be a text file so we can just open it off bat. So fopen hello meme txt, and I'm going to pass in write mode. We are going to be writing to this file, okay? So effectively now my file object is a pointer to some file, and again, they have this as some special type that we don't actually care about. All we need to worry about is that this my file object is going to be our identifier for the file that we've just opened, and we have to pass this every time we want to actually edit the file that we've opened here. So if we actually go look at the library functions again, the next thing we're going to be looking at is going to be fwrite. So effectively what fwrite does is it writes the contents of const void char buffer here to the file. So fwrite, and okay, so I should probably talk about the other parameters. You pass in the size of the buffer that you're writing, and then you pass in the difference between size and count. Oh, size of each object to write. What? There's no. I thought they fixed this. Since C99, did they remove the count? I could have sworn they had made this easier. So here they do size of. But if I'm just writing characters, so in my case, right, because this is a void pointer, so they basically say you can write any type to this file instead of just characters, which I'm actually surprised by. I thought that they had a specific, maybe fputs. Yeah, so you can do stuff like this where you're literally fputs literally writes characters to the file. But let's be more advanced and use fwrite instead, which writes arbitrary data that we have to cast ourselves to a void pointer. So let me create a string, my string, const char pointer, my meme. Someone give me a good meme. What's a meme? The name of the file is hello meme, so I have to put a meme in it. How about damn Daniel Ye? Damn Daniel Ye. What are those? There we go. All right. Good meme, right? Okay, so effectively we want to write this string to our file, and the way we're going to do this is with fwrite. So the first thing we have to do for fwrite is pass in a pointer to our data. So what is our data? Well, it is the my meme data. And this will be made significantly easier when we do. So I'm actually going to include hashtag include string.h, and I'm going to abuse the hell out of this for the length. So I'm going to have to cast this const char pointer to a void pointer, because effectively fwrite lets us write any array of anything to this, as long as we specify what the size is and everything. So the next thing we're going to pass in is the size of the type. So the size of the type here is chars. So effectively, we are going to do size of char. And the next thing it wants us to pass in is, well, how many characters are you writing? And this is why I included string.h, is because now I can just do strlen to get the length of the string, which is my meme. So that's how many characters we're actually passing it. And then the final thing we have to pass in is the actual file that we're writing to. And the file we're writing to is my meme, which we have specified already. So then finally, once we've actually written to the file and fwrite is finished executing, fwrite is actually going to return a size, and I believe the size it returns is the number of objects successfully written. So if an error occurs, it might not actually be able to write all of these objects to the file, and this size t is basically the return type here, size t, is the number of basically objects. In our case, our object type is character because we're working with a char pointer here that were successfully read into the file. So what we're looking at is, yeah, so it returns what, 0 if it's good. If size or count is 0, fwrite returns 0 and performs no other. Okay, that makes sense. Because this basically says your type is size 0, that's not a thing. And if the amount of data you want to write is size 0, then you're not writing any data. Okay. So the return value is the number of objects successfully written. So if it succeeds, then the return value of fwrite is going to equal your count. So count should equal the return value of fwrite if things go well. I'm not going to bother checking because I am lazy. And the final thing that you have to do is fclose. And this basically tells the operating system, hey, I am done with the file, guys. And the only parameter to fclose is the actual file pointer. So again, just pass my file to fclose, and it will close my file. So why don't we compile this and actually run it? So gcc, I still have this file called hello world.c, even though this is merged beyond hello world. And now if I run this, this is going to be a.exe. We should get a file called hello meme.txt, and we can see that it has successfully written, damn Daniel Yee, what are those? All right, good, good. So that was writing to a file. This is pretty straightforward. We can write anything here. So we could actually change this to be like, say instead of a char array, we wanted to actually store, you could make this like really advanced. So say that you wanted to store structs inside of a file, right? You wanted to have some struct person and save that struct to a file. Let's do something more fun and actually save a struct to a file. Let's have a person struct. And we're going to have, what does a person have? It has, we're going to, should I actually allocate pointers? Because effectively you can't store pointers in a file, because if you try reading pointers to in another program, the pointers, your program might have closed already and those pointers could be old, right? And that would be very bad. So we actually want to store the raw data for whatever we're storing inside of our struct. So I would say something along the lines of char name 50. So I'm going to have 50 characters to store the person's name here. And then what else can I do in here? I can have in age. Okay. And now I'm going to create a person object and write my person object into this file. So I'm going to say person struct person, and I'll call my person P. That'll be the name of my person. I'm then going to make my person a, let's see, I can make them, what's the name? I'll make Dan Yee be my person. So I can say per p dot name equals Dan Yee, and then I can make my age be p dot age. How old are you, Danny? 20, 21, 20, 20? Yeah, you're 20. All right. Danny is 20. We are set. Why are they yelling at me? Expression must be a modifiable L value. You're telling me that that's not a modifiable L value? Tell me that again, that that's not a modifiable L value. That's totally a modifiable L value. Okay, so what I can do instead is str copy into that. All right, strcpy. Going to str copy, what is source first or dest first? Dest is first, then followed by source. Okay, so long story short, they're mad at me because this is in the text segment, blah, blah, blah. It doesn't matter. Anyway, this has fixed it effectively. I'm string copying a constant string into Dan Yi's p name value. So effectively, this is just putting Dan Yi into p.name. The next thing that we actually want to do is store this person object inside of this file. So now I'm going to write p dot, not p dot, I'm going to pass the pointer to our p. So I have to get the address of our person object. So this is the address of, and then I cast that pointer that we've created from the address of to a void pointer because fwrite doesn't need to know what the type is. They don't want to know the type. It has to be a void pointer passed in. And then I do size of person, or size of struct person, because we're passing in a single person struct as our thing. And we are going to be passing in for our string length. We are just passing in one single person object. So it's not string length, it is one person object. And then my file. And I'm going to actually change this to write in binary mode instead, because I don't want this to write in, I effectively don't want this to try writing characters. I want this to try writing raw binary data. So now if I run this, let's go take a look at hello meme. Yes, I want to open it anyway in the text editor. So we can see here that there's some funky stuff going on. And the reason there's some funky stuff going on is because it's effectively trying to interpret what we're storing in here as everything's supposed to be stored in here as characters. So if we actually, I'm actually going to open this in the hex editor instead. So if I go back here, do I have to X out of this to have them? I want to open this in my hex editor so I can actually see what's inside of here. Yes, Tello meme in the hex editor. So what we can actually see here is, I'm assuming that this is represented as, yeah, okay. So this is actually kind of cool. So what we have here is a person object. So the person object is 50 characters, so 50 bytes of characters, right? So each character is a byte, and then an age. So effectively, the string here that we're copying in, though, is only however many characters it is. So this is what, like 10 characters, and then there's the null character on the end to specify that we're ending the string, right? So when I do this copy, there's still a ton of uninitialized space inside of this struct, and then the final 4 bytes are going to be the int. So we can see that when I write this to an actual file in here, we see that effectively these first bytes in here, we see that the Dan Yi and then the 0 for null is in here. But we also see that after this, there's some random garbage. And the reason there's random garbage in here is because when we create this object, we're not actually cleaning this object out. We are not saying, oh, all of these characters have to be 0. They're just left uninitialized in memory. And that's perfectly legal. We don't actually care about that. We can force this to clean by doing this. I believe this works in C. Please let me do this. They used to let you do this. Why are they yelling at me now? Expected a... This used to be completely legal. Do I have to say this? Yeah, okay. So effectively, there's this special syntax here that basically says, okay, we're going to declare this object as empty, and this will force 0 all of the bits for this entire struct. So now if I run this again, we should see that instead of having random garbage in hello meme when we save it, this should all be zeroed out. All of this up until this final 4 bytes. And you can see these final 4 bytes as an int 32, which is what this actually is. It's the number 20, right here. So we can see that actually, yeah, it's literally storing this entire struct in a file. And then we could, if we wanted to, read this file as a struct into a struct object, right? So this is called serialization. In Java, this is kind of a big deal. They actually like have serializable interfaces and everything. In C and C++, it's pretty straightforward. You literally just say, yeah, smash all of the bits of that our class or our struct represents into a file, and boom, you're serialized. Problem solved. Obviously, you have to do it yourself, but this is kind of fun to be able to write your entire class object into a file. The only issue is you can't have any pointers here. If you try and put pointers to things, you're going to start crashing things, because if you try and load a struct that has a pointer as a member, that pointer may have changed when you reran the program, and you're crashing everything and probably getting seg faults because you'll be trying to access pointers that you no longer own. Anyway, so I just wanted to demonstrate, though, that I think this syntax, when you declare a struct like this, should actually clear it out. What are they mad about? What are you mad at? I changed that. Hang on. GCC, good. A.exe. And let's see, does this, yes. So this syntax now sets everything else to 0 in the struct, besides these ints right here. And then you can see here we have Dan Yi is the first however many bytes, followed by the null character, right? So this is pretty interesting. We can easily serialize any of our C structs just using an fwrite. And we can literally save a struct to a file. Very straightforward in C using fwrite. So let's see. Let's try now reading Dan Yi struct. So I'm going to call this the Yi struct. Yi. And now that this is no longer a text file, this is like a binary file, I'm going to create my own file type called Yi. So this is the Yi file type. It's not bullying, Dan. We love you, Dan. If it was bullying, I would I'd have it be like Dan cringe. Bully Dawn instead. Okay. Dawn, and the file extension is going to be goth. Dawn.goth. And I'm going to, instead of person, I'm going to have it be goth, the goth type. And then I'm going to have there be a should I do it? I'll do an enum, and then I'll have an enum up here. Enum shade of gray. Actually, no, goths are like black, but there's like different types of black that are all different. What should I do? Enum. I can do an enum for type of depression. So like there's a lot of different depressive disorders. So I'll have a disorder enum. And we'll put in major depressive that I don't think that's how you spell it. That's fine. Minor depressive. What else do we have? PTSD. That's a disorder. I don't know if that's a goth disorder though. I'll have, yeah, okay. So you have to have an enum disorder as well. Sure. And I'll call this disorder. There we go. Okay. So this is a pretty successful struct we got going here. Seasonal effective. Can I just type SA? How do you spell seasonal? SEAS on all AF active. There you go. If anyone is still watching this after 2 hours, there is no this isn't an accredited C workshop. There shouldn't even be a recording. Okay, so it's setting each of these. So this is 1, 2, and that's 3. Okay, very nice. So we're going to create this struct, and I'm gonna change the name down to like 20 bytes because we don't really need anything more than that. Okay, so person P, and I'm going to copy the name in Dawn Pog, and then age. Dawn, you're like what, 20, 21, 22, 20, 21. Yeah, I was at your birthday. Okay. Let's see. And it's no longer struct person, it's struct goth, and we have this special goth file extension to let us know it's a goth file. Then we're gonna do p dot disorder is going to be equal to, so we can I don't know, what do you want? I'll give you seasonal effective. Okay, so now if we actually store a goth struct, let's just make sure we can store a goth struct really quick. Struct goth cast, good. Compiled. run, and here is the dawngot.goth file. We're going to open it in a hex editor, and we're going to see right here, first things first, we have the name, which is dawnpog. Then we have a bunch of zeros because we give 20 bytes. And then we're going to see right here an int, and as you can see, ints are 4 bytes, right? So we're storing 21 as the age, this is the age, and this is the disorder type stored as an int because they're storing our enum as an int effectively. So this is basically, this final thing here is 3, and this 3 corresponds to one of our enum values, which is, in this case, seasonal affective. So now let's actually read out, why don't we actually do a read from this file? So we've closed the file. Let's write a new program that reads from this. And technically what I should be doing here is actually putting goth and disorder inside of a header file, and then we would be able to use that to basically get this. But instead, what I'm going to do is, we already have this all written into this file, so I'm just going to delete the code. I don't need this code anymore. And effectively, I'm going to open this and say, instead of write binary, now we're going to read binary instead. So the function now for us to actually be able to read stuff is the fread function. So what we're going to do with fread is, so because we were able to write, hang on, let me go back. fread, where is my nice fread? We can talk all about fread. So the first thing fread takes is a buffer. So this is a void pointer basically to a location that I'm going to be reading things into. Then again, the size, the count, and the file. It's basically exactly like write. So what we're saying is, okay, effectively, we know for a fact that there's one goth object in this file. But we might not. There might actually be multiple goth objects in this file, in which case we would have to parse the file first and have some additional piece of information in this file that told us how many goth objects. And now we're getting into file type design, where you would actually be designing your own file type to put things into. And this would include different parts of the file that specify how many objects are in there, different segments of objects, and this is a huge area as file type design. But we don't really care about file type design. We just know for a fact, because we've already written one object into this file, that effectively it should be very easy here to read things in, because we know exactly how many objects are in this file, because we wrote those in ourselves. So if we know that a goth file only stores one goth object, this is going to be very simple. I think they call it, what, deserialization? I don't know if it's unserialization. I think it's deserialized. So we're going to deserialize the goth object into a real goth object here. So I'm going to say, all right, so we're going to read, it's a void pointer. So first things first, I'm going to have to create a goth object that we're going to actually be storing things in memory. So this is going to be goth g. And effectively, here we're going, oh, you have to type out struct. Here we go. Struct goth g. And now I'm going to say, all right, we're going to cast the location of g to a void pointer. And this is the destination, right? This is where we're actually going to be writing the stuff to. So fread reads into a buffer. But in this case, we want our buffer to literally just be the goth object. So then size of the size of our type, which is size of struct goth. Struct goth. I can't spell. There we go. And then the number of goth objects, 1. And finally, the file that we want to talk to, which is my file from fopen. Okay, so now we are going to, so effectively after this is done, we now have a fully populated goth object. So let's actually see if we can use our goth object, how we would want to use our goth object. So let's write some meme code to actually print out. We can say printf I am goth, my name is, and then %s, and then print out g.name. Then we can do something like, okay, so my name is S, and I am %d years sad. G.age. G.age. Okay. So this is going to print out the name first and then the age. Beautiful. And then the final thing that we want to do is print out the disorder type. And to do this, I'll do a cringe switch statement. Switch expression is going to be g.disorder, and we are going to do a case statement based on all of the different disorder types. So if you have disorder 1, so in the case that g.disorder is major depressive, it's going to print out, probably do a new line for this. Let's see, code. I'm going to just copy disorder. There you go. Sure. Gonna pretend that that's spelled right. Then we're gonna do. You know what? I don't care enough to do the type the other ones out, so I'll just put them in as defaults. So what are the other ones? Actually, I can just literally have them all in as default. I don't even have to specify them. I have some other sad thing disorder. Okay. All right. So let's actually see if this works. We should be able to get this to work. a.exe, and we can see that it has successfully read from the serialized file. My name is Don Pog. I'm 21 years old. I have some other sad thing disorder, which is exactly what we expected. So effectively, we are reading a fully serialized object here, a binary serialized object. We've invented our own file extension, the goth file extension, and we have read from a file with it. So this is basic file IO, pretty fancy, not gonna lie. I do like doing serialization in C. It's actually kind of cool because you can actually then, like, go look at it. It actually makes a lot of sense. It makes more sense than stuff like Java, where you're always like guessing what the structure is. But no, this is really straightforward. The order in which you declare things inside of your struct is the order that they appear in your serialized file if you write them that way. So literally, if I go in here and look, it's literally like 20 characters followed by an int, which is 4 bytes, followed by an int, which is 4 bytes. Like very, very straightforward. Obviously, again, you can screw this up because of alignments and various legal alignments, but it's not really our concern. All that matters, we don't really care about what's actually in the file because we're not actually writing any fancy our own file, like our own real file specification and parser. All we have to care about is, yes, we've written a single object to this, and we are guaranteed to be able to read an object out if that's the way that we wrote the object in with an F right. So that's basically file IO. I mean, we could probably do something more fun where we write, like, text, but I think it's more fun to serialize objects because I think object serialization is way more useful than writing text to files. Writing text to files is like, baby steps. Writing objects to files is like, oh, now we're talking. Now that's a real application. Like, you can do a lot of stuff once you can save objects and then load objects from disk. That's like, wow, we fancy now. Okay. So that's I think that's everything I wanted to discuss for tonight, and just in time too, because we are at 9:57, which is 3 minutes ending 3 minutes early. But it's probably not actually going to end 3 minutes early because we need to discuss homework for tonight, which I actually didn't plan out. Probably could do some fun stuff. I could have you create your own file type and say, "Hey, I'm gonna, store." I could have you create your own struct and basically write your own struct to the file type or to a file. Create your own file type for that, and then read it back in and print out some information like I've done here that isn't the goth type. That's kind of boring compared to the matrix effect that I had last night. So I mean, I could tie those two projects together into like a final project where I have you have your settings be a struct and you're able to edit your settings on the fly. There could be some menu, and then you actually have to save the settings struct and then read the settings struct in every time from the file every time you load the program up to see, what color you want your matrix to be, blah blah blah. That could be fun. Probably even the struct is overkill for that. You could literally just do like a text file for that has a list of settings. So that could be fun. Yeah, why not? Why don't I just do that? So I'll say, in continuing from the matrix project that I laid out last night, I'll have tonight's project homework be Let's see. Strings and things was yesterday, 2 days ago. All right. I don't know what this was. So the homework for last night with Enums and Unions was matrix effect. And I guess we're going to tie matrix effect up with what we'll call. So the homework for tonight will also be matrix effect with the addition that settings file for. And so for those, I think I showed off the GIF, but I'm going to show off the GIF again. So effectively, there's quite a bit we can do with this. So think about the different types of settings you might want for something like this. The number one thing that comes to mind is settings for colors, right? So you would represent that as an enum internally, what color you want these little lines scrolling down to be, right? And you would read the enum out from a file, right? And then check if it's valid, blah, blah, blah. That's the first thing. The other thing I can think about is the rate at which these things fall down the screen. So we're talking about like effectively these are going at like 1 character per frame is what it looks like, but you could have it do 2 characters per frame, so they could be going much faster. You can change the density of them falling, so you can have more. So there would be like a random function to determine when new ones are created, blah blah blah. That's fun. So that's a good setting right there. You can really come up with your own settings for this, but the primary ones that I'm thinking of are color, fall speed, and then basically trail length, the length of each of these snakes. So I'm going to put these down here with settings for trail length, color, colors. How about I have this be an array and you read in multiple colors at the same time for different snakes, so snakes can randomly pick between different colors. That would be fun. Okay, so trail length, colors, and what else? Got to be something else fun I can do for this. I had one. Trail length, falling speed, and snake density, and density, effectively. Density. Okay. So I went over all of this, keywords, blah blah blah. Basically, we know printf, scanf already. File IO. We can go over fseek, but we don't need fseek. That may or may not be on the exam. I'm gonna look over all the LinkedIn questions tomorrow and see if there's anything we don't know, and then we'll review, and then you can take the exam at like 9 probably is what we'll do. Okay. Anyway, so this is just a project idea, is the matrix effect with settings where you're reading files. Anyway, I think that's it for tonight.